Kids, today we are going to take notes on exponential growth and decay, which are just applications of separable differential equations. And I'm going to teach you how to first recognize that you have it. That's kind of prior knowledge, but also how to avoid calculus legally on the AP exam. What that means, and think about what that means, if AP is going to allow you to skip calculus, then they're testing, what they're going to test is the recognition piece. Do you recognize the separable? Could you set it up? Can you translate the words into the setup? So that's what I've given you here. I'm not actually, all I'm doing with this is just giving you an example of the words that you're looking for in these kinds of equations or these kinds of problems that clue you into you've got exponential growth or decay. So firstly, the number of bighorn sheep in a population increases. So I hope you know that means growth. At a rate, that is a derivative, that is proportional. We call constant proportionality K, to the number of sheep present. The original population. This is true. It doesn't have to be bighorn sheep. I just think bighorn sheep is a fun word, right? Population of living creatures. Also money, right? Radioactive material decays at this exponential rate, right? Money, if you're in an interest-bearing account, lots and lots of things in nature, in our real world, grow at an exponential rate or decay at an exponential rate. So what that equation looks like is this. This is a differential equation. How do I know it's a differential equation? It has a derivative in it. It is a derivative with respect to time. There is a constant of proportionality, but look at the dependent variable, right? The population changes at a rate. The population changes. Population, why? Population changes at a rate that is proportional to the original population. That's exponential growth rate equation. But the key is recognizing, whoa, that is a separable differential equation because I have a derivative, which is a rate of change, and it is proportional to the original amount. The rate of change is proportional to the original amount, right? I see you, separable differential equations. I got you, right? You can't fool me. Be careful. Think about that example I did with you in the last class, right? Where I just called this a P. And then I had a capital P on the right side. If the dependent variable is on the opposite side of the equation, and it's a differential equation, you have a separable differential equation. So let's solve this. Let's pretend this is the rate of change of the bighorn sheep, and it is increasing, right, at a rate that is proportional to the original amount, or the amount present. So what did I just do? Right? I am separating. I recognized the y is on the wrong side. The dependent variable needs to go over to the left side, and then I multiply both sides by dt. Now, what am I going to do? Right. So this is easy. This is y to the -1. And this is, right, that's not t. That's just a constant. Pretend it's 5. Pretend it's 7. Pretend it's 2, whatever. How do you integrate a constant? Right, so here's the ln of y comes from y to the negative 1. Right, that's what you're doing there. And then, right, you could think about this constant osmosising out here. And then you're just integrating dt, which is really t to the 0. So you have t to the 1 over 1 times that k plus the constant that's wrapped up from both sides. Now I do want to get y by itself, so I'm just going to e to the both sides. And then I'm going to use my law of exponents here, remember? X to the third times x to the fifth is x to the 3 plus 5, x to the 8th, right? See the exponent twice with multiplication in between, write the base once and add. Go backwards. If you see the base once with a sum in exponent land, you can write the base twice with multiplication in between. That's what I'm going to do. But e to the constant is still a constant. Oh, also I got rid of absolute value, and we've done this before, but right, just to make sure to formalize it for you, I got rid of absolute value because that just means that you had a positive or negative. But remember, a positive or negative constant is still a constant. Usually we call that capital C. This time I'm calling it capital A. Doesn't matter, right? It's just a constant. I'm just shifting the lines up. But if I'm interested in when time starts, at t equals 0, this is my original amount. So whenever I decide to start the clock, so let's say, I mean, there's been bighorn sheep forever, but let's suppose like in this right certain area, I count that there are 10 bighorn sheep, right? And then I start the clock, and because maybe there's a disease, so I want to see what's happening to the population as a rate of a disease, or maybe I don't. Maybe there's nothing. I just want to investigate how does the bighorn sheep population grow over time. I studied it at what I call time 0. There were originally 10, and now I'm going to keep coming back and see how many there are. So at time equals 0, we call this the original amount you counted at whenever you decided to start time. Notice what happens when I put in 0 for t. I get e to the 0, which is just a 1. Therefore, my original y sub 0 is the constant. So do you see how I can replace this? Given exponential growth where you start the clock at some arbitrary time, right? You can't actually I mean, time going back is infinite, right? Till the Big Bang, I guess, whatever. But this is the solution to given an exponential growth rate equation where the rate of change of y is directly proportional to y. We solve that equation to get y by itself, and it's yekt. Yekt, right? That's what I call this. This formula is worth writing down. The solution to any exponential growth rate separable differential equation is yekt. And you don't have to do all that calculus every time. Okay, AP allows you to go directly from this equation to here without showing any work. Those of you that can recall from Algebra 2 or from AAF, I gave you this equation when I taught you PERT, right? I just said, hey, if we have an account, we have $1,000 and we put it into a bank that accrues interest, right, continuously, E naturally comes out of that math. And I gave you y equals PERT. I just called the original amount of money P was principal. This is where PERT comes from. And your R is your constant of proportionality, OMG. And if you remember, if you had me, I told you that I would explain this math to you someday as to where it came from. This is that day, right? And by the by, E did come naturally out of this math, right? Do you remember where E came from? E came from the fact that I had a separable differential equation where I ended up with y to the -1 on one side. Integrating y to the -1 gives me an ln. Trying to isolate y out of ln meant I had to E, right? So actually, the natural log came naturally out of this math, and then I had to E to get y by itself. OMG. So when you're in algebra 2 and if you were that kid raising your hand going, well, I really need to know why and this and and where this comes from. Oh, well, I couldn't tell you until you learned separable differential equations. So there. That's my rant for the day. All right. But right, sometimes math is the long game, right? You just have to do it and practice it. And then understanding the concept might take years before you get where something comes from in math. That's just the nature of mathematics, which is part of the reason I believe it is beautiful. So there you go. The formula for exponential change is yect, where that y sub 0 is the principal amount, original amount at time equals 0. When k is positive, that's exponential growth. Slide swoosh. When k is negative, that is exponential decay. Swoosh, slide. So again, if you are asked to solve the separable differential equation of the form dy over dx or dy over dt or dp over dt or whatever, where the rate of change of y is equal to constant proportionality times y, you can solve that. It is a separable differential equation. It is not difficult to solve, but you don't have to. AP allows you to go directly to the solution. Now, you are going to have to do some math because somebody's going to tell you about, well, how many initial bighorn did I have? And what is the constant of proportionality? I don't know K. So the math that you're actually going to have to do is mostly algebra 1 and algebra 2 solving for your constant proportionality. Yet. So I'm going to go through a couple of equations that your book uses, right? That you might need to do some of the book homeworks. If you need these equations on AP, because there is no formula book, AP will embed them in the problem. So your homework problem does have some money banking problems and deals with continuously compounded interest. This is a separable differential equation. Really, right? This is the amount, is the initial amount. This is where that came from. The amount I get is, this is yect, right? The solution to a differential equation. This is y is equal to y sub 0. This isn't e to the t yet because I haven't dealt with adding the interest continuously. I've only dealt with it adding k times per year. So to go from here to continuously takes a limit. But of course, there aren't actually people in the bank doing the limit of this, right? This is a limit as the number of times goes to infinity. But what that turns out to be, since the interest is proportional, and the interest is the rate of change, is proportional to the amount present, here's what you get. The amount is the amount you have over time is the initial amount times e to the RT. This is a solution to the differential equation where the rate of change, which is your interest, is proportional to the amount present. Of course, I call that Perp. Radioactive decay, if you're in chemistry, you probably have dealt with this formula in physics as well. If K is negative, we are talking about decay. And that way we can always talk about the constant proportionality being positive when we just put this negative here. Half-life means that whatever initial amount you started with, I want to solve for T after half of it is gone. So that's this equation, right? This is the amount I have left over time but I replaced y with half of the original amount, and I'm going to solve for t. So that's not calculus, right? That's algebra 1 and algebra 2, right? ln and e undo one another. Log rules, see the log twice with division, subtraction in between. Write the log once and divide. Or, of course, recognize that the ln of 1 is 0. Divide off the negatives. And the half-life of material, radioactive material that decays over time, is ln of 2 over k. That's probably a formula, half-life formula that you got in chemistry or physics. You might have to use it. You will have to use it in some of our textbook problems. So this is the handout that you want to access while, right, it's linked on our page. And this is a typical book problem. So I want to highlight the pieces that are important because there's an awful lot of words here. A car coasting to a stop is proportional to the object's velocity. So the rate of change of velocity is equal to a constant of proportionality. Now, this constant of proportionality, don't get thrown. This constant of proportionality does have this m with it. K over m is the constant of proportionality, but your mass, right, if you're talking about a car, its mass is constant over this time, right? We're going to talk about an ice skater, right? So this is a separable differential equation for any moving object. And we're just in our problem, we're going to talk about a skater. Well, her mass is constant throughout this problem. If you're talking about a car, the mass of the car is constant. So this m is not a variable. So notice here what part A is asking you. And what you say is, no. Nah, I don't want to. You don't actually have to solve the separable differential equation because it is of the form, the rate of change of velocity is proportional to velocity. Okay? I don't have to solve that. I just have yet. So the first thing you need to do is recognize that that really is a KY problem, right? Again, all that's different is that you have a constant mass. There's a negative out front because we are coasting to a stop. So, right, the moving object is slowing down and then stopping. I don't have to solve because I recognized yet. So there's my yet, right? Y is equal to y sub 0 e to the, in this case, I'm decreasing, so negative kt. I called my y velocity in terms of t. I called my initial y, initial velocity. And remember, my k is divided by the mass of my object. Done. Done with part A. Check. That would only be worth 1 point on an AP rubric because you don't have to solve it, even though the direction said solve. But you recognized KY. I see you, King. It's supposed to say C. I see you. So, part B, 50 kilograms. The units tell me that's the mass. The mass is constant. I'm just going to plop that into the equation and forget about it. Is skating at 7 meters per second. That's the first velocity I know. Okay, first velocity when they started time, when she started to coast, she was going 7 meters per second. The units told me that was velocity. So I filled in the equation with the 7 and the 50, right? From part A, initial velocity when she started to coast, and she had a mass of 50 kilograms. Notice that that is one equation with 3 unknowns: the velocity after a certain time, the constant of proportionality, and time. Look at what information they gave me, though. They gave me a point. After 1 second, she had slowed down to 6.66 meters per second. So I plugged in the point. T of 1, V of t of 6.66. What can I do now? Right? I can solve for K. Now, I did some math here, right? But I had this, you would have a calculator. So I did 6.66 divided by 7, and then I ln both sides, and the ln e went away, and I had negative k over 50. And so I multiplied this by negative 50. And that's how I got k to be 2.490. I wrote down 3 places past the decimal, but I used my calculator to store all the degrees of accuracy because K is not the final answer. It's the final answer to this problem. And yes, you can put equals. They won't take off points if you put equals. I just put approximate because in the AP directions, it does say that you're expected to maintain degrees of accuracy throughout a problem, and part B is not the end of the problem. So I wrote down 3 decimal places because that was the answer to part B, find the value of K, but then I stored that in alpha K. Of course, you don't have to store it in alpha K. I was just being cute. So how long is a time issue? Will it take the skater to coast from her original to 1 meter per second? Plug and chug, hun. Plug in 1, solve for t. Now I kept k here, but I wrote what k is already, right? So I don't have to bother writing it again. I can just use k, and when I'm writing down, just saves me a couple, nanoseconds. Divide by 7, ln. I got an answer that I wrote 3 places past the decimal, and the time units. So that's how long it takes her to coast from 7 meters per second to 1 meter per second. Okay, I solved an equation for time. There's no calculus in that. Here's the kicker. It's part D for a reason. How far is a distance? How far would the skater coast before she comes to a complete stop? Well, when she stops, the velocity is 0, right? So why can't I just solve that equation for 0? You're going to divide by 7 and get 0, and then you're going to what? You're going to try to take the natural log of 0, and you can't do that. That's called domain issues. What do I do then? I got to show some math. What do I do? Look at what I wrote. The question they asked me is distance. What equation did you have here? What equation is this? This is the velocity equation. How do you go from velocity back to distance? What math have you just learned to do that? I tried to use my velocity equation and the algebra wouldn't let me. I can't take the natural log of 0, so I want distance. Oh, snap. The distance in terms of time is the antiderivative of velocity, right? Right? dv dt is equal to the derivative of position. I could call it d, I guess. The derivative of position is velocity. I want position by itself, or distance, I guess I should call that distance, dd, that looks kind of weird, is anti-differentiate. How do you anti-differentiate e to the stuff? U substitution, baby. U is this stuff. Oh, I don't need the T there, do I? What is the derivative of that stuff? Oh, I guess I do. Silly, sorry. The derivative of that stuff is negative k over 50. Get the dt part by itself. I osmosis the 7 outside. I replaced dt with negative 50 over k du, osmosis the negative 50 outside as well. The integral of e to the u is just e to the u. So distance is equal to 7 times negative 50, which is negative 350, over k. Remember, I know my k. I just didn't write it every time. E to the negative k over 50t plus c. Oh my goodness. So that is the distance in terms of time. How does that help? I don't really have a point to plug in for c, right? To solve for c, but what am I going to do? How far will the skater coast before coming to a stop? So she spins, she starts, her distance reaches a L word. Limit. So sorry, I did a step before. I do have a point to solve for C, 0, 0. Right, at time equals 0. How far she had coasted is 0, right? So I plugged in 0, e to the negative something times 0 is e to the 0, which is 1. 1 times negative 350 over k is negative 350 over k. C is equal to negative 350 over k is C plus negative 350 over k is equal to 0, means that C is equal to 350 over k. So there that is. And now, jumped ahead of myself. Now I can't plug in. I want to know what is, I don't know the time, right? I don't know the time and I don't know the distance, but she's going to eventually go to a stop. So I'm going to take the limit as time goes to infinity, which again, in physical reality, she will actually stop. When you take the limit of, this is just a coefficient, right? Coefficient e to the negative. That is a swoosh slide. So as t goes to infinity, what does this graph do? goes to 0. So as the time goes to infinity, the limit of this distance formula is 350 over k. And remember, my k is 2.490. So I did 350 divided by alpha k, and I got 140. 3 places past the decimal, and the units. Crazy, right? Distance coasted at time 0. Oh, other way around, silly. Time 0, distance coasted. That's how I got my C. Took the limit, e to a negative, swoosh slides, asymptotic behavior. The asymptotic behavior is at the horizontal asymptote. Because that e to the negative graph had gotten shifted up by 140-ish units. Crazy, right? All right, so that's exponential growth and decay. In our next live session, we'll do an AP problem with exponential growth and decay. And we'll show you how, because you're going to practice with book problems, we'll show you an AP problem where students had to access this information. And I have to say that recently, most of these kinds of problems where you have to recognize and deal with exponential growth and decay have been on multiple choice and not free response, because after all, there's not a whole lot of calculus that you did in this problem, just there at the very end. All right, I will see you in our next live session.